Hello everybody, welcome to today's video. Today we will be covering the double angle, half angle, and power reduction formulas. So we'll just some more identities or formulas to add to our list of the ones we've got so far. And then we'll use them to solve some problems here. So we will hop right into it with the double angle formulas. So what we're going to do is derive these formulas like we have been. And by double angle, I mean things that look like sine of 2 times theta, or cosine of 2 times theta, or tangent of 2 times theta. And then we can use these identities if we know the values of theta to figure out what these double angles must be. So what we're going to do here is just use the sum identity that we had before, and we're going to make the angles the same. So what this is saying is we're going to set alpha equal to beta, and in fact we're just going to call it theta, just so we can get things in terms of theta. I could have just picked alpha or just picked beta, but notationally we usually use a theta here. So what I'm going to do to derive this double angle formula is I'm going to take the sine of alpha plus beta, but I'm going to write this as theta plus theta. So I'm just letting those two terms that are being added together be equal to the same value here. And if I rewrite what the sum identity tells us here, we would be getting sine of theta, cosine of theta, remember alpha and beta are the same now, they're both theta, plus sine of theta, cosine of theta. And if I simplify what I have here on the left-hand side, I have sine of 2 theta. On the right-hand side, I have exactly the same thing being added to itself. So I have 2 sine of theta, cosine theta. So there we go. Here is our double angle identity. If we know something about sine of theta and cosine of theta, then we could figure out the sine of 2 theta here. We could double that angle. Okay, so there's sine. Next we'll get cosine by doing the same thing. We're going to take cosine of not alpha plus beta, but of theta plus theta, so that the terms that are being added are exactly the same. So just filling in the details here, this is just our regular sum identity for cosine. I could write this as cosine theta minus sine theta sine theta. And as I simplify this, I'm going to get cosine of 2 theta is equal to cosine squared theta minus sine squared theta. Now notice that looks dangerously close to the Pythagorean identity, but here there is a subtraction in between the two, and the order definitely matters for subtraction instead of an addition. But we can use the Pythagorean identity to get a few more forms of this cosine of 2 theta. So remember that the Pythagorean identity says cosine squared theta plus sine squared theta is equal to 1. And we can rearrange terms here. We've done this in the past, so I could write this as perhaps cosine squared theta is equal to 1 minus sine squared theta. Or I could write that sine squared theta is equal to 1 minus cosine squared theta. So these are all just rearrangements of the Pythagorean identity. And then I can substitute what I know that cosine squared theta is, or what I know sine squared theta is, into our double angle identity here. And we'll get a few more different looking forms that will be useful. So the first thing I think I will do is substitute in this cosine squared theta. So I will get that cosine squared theta is 1 minus sine squared theta minus sine squared theta, which is going to give us 1 minus 2 sine squared theta. So here is another version of our double angle formula. I should go back and box that first one. So here is our formula that follows just from plugging things into the sum identity. We can do a little bit of rearranging here to get this other identity here. And then if I wanted to instead plug in sine squared into our original formula up here to this sine squared, what I'm going to get is cosine squared theta minus, and now let me make sure I'm using parentheses here because I'm going to need to distribute this negative. But I know that sine squared theta is equal to 1 minus cosine squared theta. Whoops. And so as I rewrite this, I would get cosine squared theta minus 1 plus cosine squared theta, which is going to give us 2 cosine squared theta. I can write that a little better. 2 cosine squared theta minus 1. So here is our last version of this identity here. So sine of 2 theta just has its single identity. Cosine of 2 theta happens to have 3 different forms, and each one might be more beneficial depending on the situation that we're in. So there we go. We still need to do tangent, but we're out of room on this slide, so let's go to the next page here. And I've got a summary of what we had found on the previous page, that sine of 2 theta is equal to 2 sine theta cosine theta, and that the cosine of 2 theta is either cosine squared theta minus sine squared theta, or we could maybe write it as 1 minus 2 sine squared theta, or 2 cosine squared theta minus 1. So those are all different forms of the same identity there. Okay, and then for this last one, for tangent, we're going to use its double angle, I'm sorry, not its double angle, but its sum identity. And again, we're going to let theta be equal, or alpha be equal to beta equal to theta here. So I'm just going to be rewriting this as the tangent of theta plus theta. And so plugging things in here, we're going to get tangent of theta plus tangent of theta all over 1 minus tangent theta, tangent theta. So I'm just plugging in thetas for alphas and betas. And what we are going to get here is that the tangent of 2 theta is equal to 2 tangent theta all over 1 minus tangent squared theta. So here is our identity for the tangent of 2 theta, our double angle formula for tangent. Okay, now that we've got them derived, we can use them. So here we've got our double angle formula here. Or all of them for sine, cosine, and tangent, just listed out so we can use them. And what we're given in this example is that the tangent of theta is equal to -3/4, and that theta is in quadrant 2. And we want to find all of these double angles here. So what we're going to do first is draw a picture. I'm going to get my unit circle on here. So there's our unit circle. We know that this angle is in quadrant 2. So let me just rough this in here. And we'll say that this is our angle theta. And I know that its value is -3/4. So just thinking about our reference angle here in this reference triangle, I want opposite 3 over adjacent, which is 4. And the negative goes with the 4 since that is... the cosine part of this is the negative portion. Okay, so this gives us a little picture here. I can tell just since this is a 3, 4, 5 triangle that the hypotenuse must be a 5 there. You could just use the Pythagorean theorem to see that straight away, but hopefully we have recognized this pattern by now. So this tells me that I can find the sine of theta. It's going to be the opposite over the hypotenuse, and I can find the cosine of theta. It's going to be the adjacent over the hypotenuse. So I now have explicitly written out the sine of theta and the cosine of theta because I will need them in order to find the double angles here. So let's go do that portion now. Now we've got all of the background information that we're going to need from the problem. So cosine of 2 theta is going to be 2 times the sine of theta. The sine of theta is 3/5 times the cosine of theta, which is -4/5. And now we just multiply things out. We will get, maybe I'll just switch colors again. We will get 2 times, if I multiply my fractions together, I'm going to get -12 over 25. So this is going to give me -24 over 25. So here is the value of the sine of 2 theta. Now we don't know what theta is, but we do know that the sine of 2 theta is -24 over 25. Okay, next we'll find the cosine of 2 theta. So again, we'll probably want to use these values over here, but we have a decision to make. Which version do we want to use? Do we want to use the cosine squared minus sine squared version? Do we want to use the 1 minus 2 sine squared version? Or do we want to use the 2 cosine squared minus 1 version? I think one of the bottom two makes a little bit more sense since we wouldn't have to square two fractions here. It doesn't really matter though. I think that I will pick the 2 cosine squared theta minus 1 version. That just seems to maybe be nicer. You might disagree and pick a different version. They should all give us the same answer here. But I know that the cosine is -4/5, and I want to square that, and then I want to subtract 1. So this is going to give me 2 times 16/25 minus 1. So I'm going to have 32/25 minus, and let me rewrite 1 as 25/25, so that this gives me positive 7/25. So there we go. There is our double angle for cosine, the cosine of 2 theta, 7/25. All right, last we will get tangent here. Maybe just put in some visual separators. Okay, tangent of 2 theta, so we only have one version of this formula here, but we're going to actually need to figure out what the tangent... Oh no, we know the tangent. The tangent is -3/4. We were told that from the very beginning, so we don't need to do any sort of back work here. What we do need to do is just write this as 2 times the tangent of theta, and the tangent of theta is, again, -3/4. And then this is all over 1 minus tangent squared, which is -3/4 squared. All right, and now we can simplify this. This is going to give us -3/2 in our numerator, and it's going to give us, I know it's going to be a 1. I'm going to rewrite that 1 in just a second, because this is going to, on the right-hand side, give us 9/16. So just to get a common denominator as I'm writing things here, let me write 1 as 16/16. So that I get -3/2 over, that should give me 7/16, which is going to be -3/2 times 16/7. We're going to get some reduction here. This will reduce to 8, and we're going to get -24/7 as our answer here. So there we go. We have got the tangent of 2 theta there. Again, we don't know what theta is, but it doesn't matter. We were able to figure out the sine and the cosine values, and we can do that. We can use those to figure out the double angles for these here. Okay, next we're going to use these double angle formulas to verify some identities. So these identities are always an important part of trigonometry. So I think what we're going to do here is start with the right-hand side. That looks a little bit more complicated to me. We could start with the left-hand side since it has a 2 theta in there. Maybe that's the new thing, so that looks a little more complicated. But I'm going to start with the right-hand side here. So this is going to give me, as I square this out, what this says is sine theta plus cosine theta times sine, sorry, I'm leaving my parentheses off my thetas this time, since there's already so many parentheses. So sine theta plus cosine theta times sine theta plus cosine theta. And as we multiply things out here, we would get sine squared theta. This would give us 2 plus 2, but it doesn't matter which one comes first. Sine theta, cosine theta, and then at the end here we would have plus cosine squared theta. Now I'm noticing there is a Pythagorean identity in here. I've got sine squared theta plus cosine squared theta. That's just going to give me 1. And then I've got plus 2 sine theta cosine theta. Well, now I'm recognizing one of our new double angle identities here. So I know that this portion here is plus sine 2 theta, and we still have that 1 in front. And this is exactly what we were trying to find over here, 1 plus the sine of 2 theta, so verified. This is a true identity. All right, moving on here. Now we're going to look at the power reduction formula. So here, if we're in some sort of situation where we have sine squared of theta, and that isn't as helpful, but we know something about the double angle, we can use that instead. So here we're just taking the sine function, which is something squared, and reducing it to something in terms of cosine that's not squared. And we're taking cosine squared and reducing its power to something that's not squared, and we're taking a tangent squared and we're reducing it to some trig functions that don't have squared. So this is sometimes a helpful thing to do. So we will derive these formulas from all of the different versions, or a few of the different versions for that cosine of 2 theta. So those just kind of going back here, we're taking these. This is why we started with the double angle formula, because we're going to use it, but we're going to take these 2 versions here to get these power reducing formula. So that's what I have here underlined in the yellow. So let's go through these. We're just going to do a little algebra here. There's nothing too crazy going on, but I might add 2 sine squared theta to both sides. And then I would get, well, 2 sine squared theta plus cosine of 2 theta equals 1, and then I would subtract cosine of 2 theta from both sides, leaving me with 2 sine squared theta equals 1 minus cosine of 2 theta. Then we would divide both sides by 2, and I think now we'll have the claimed formula. So this is just a straight algebraic rearrangement of the double angle formula for cosine, and we'll get sine squared theta is equal to 1 minus cosine 2 theta all over 2. So there we go. As promised, there is the power reduction formula for sine. So we'll do the same thing here for cosine of 2 theta. This one, I think, involves a little less algebra, because I can add just 1 to both sides here. I can skip kind of one of these other steps that I did for sine. And I would get 2 cosine squared theta equals cosine, let me write it the other way so it matches, 1 plus cosine of 2 theta. And then we'll divide both sides by 2, and we'll get that the cosine squared of theta is equal to 1 plus cosine of 2 theta over 2. So there we go. There is our power reducing formula for cosine. Maybe actually, let me make these a little bit smaller. All right, now we've got some room here. So to get the tangent squared, we're just going to use what we have on the other side here. So I know that tangent squared theta is equal to sine squared theta over cosine squared theta. So I can just literally write in what I know sine squared theta to be, which is 1 minus the cosine of 2 theta over 2. And this is all over the cosine squared, which is 1 plus the cosine of 2 theta all over 2. Now you can think about multiplying by the reciprocal here, but just to cut to the chase, those 2's are going to cancel, and what we're going to have left is what we're going to have left is 1 minus the cosine of 2 theta over 1 plus the cosine of 2 theta. So it's really just the 2's and the denominators here that are going to cancel out, and we're just left with kind of the more interesting portion here of 1 minus cosine of 2 theta, 1 plus cosine 2 theta written as a fraction. So there we go. We've got our power reduction formulas. So let's go ahead and try to use them. All right, taking a look at this example here, we're asked to rewrite cosine to the 4th power of x as an equivalent expression that does not involve any powers of sine or cosine greater than 1. So we've got a cosine to the 4th power here. We need to get that down. So luckily we have this power reducing formula. So, you know, if we knew something about the cosine and the sine, or I guess just the cosine of x, or its double angle, then we could use this to write things out how we want here. So I'm going to start by writing this as the cosine squared of x, all being squared. Hopefully you agree that that says the same thing. I'm just viewing this a little bit differently here. And now we'll just use the power reduction formula for cosine squared in our next step. So we will get on the inside here, and we still have the square here, but now we're going to get 1 plus the cosine of 2 times whatever our input here, which is just x, so nothing too interesting going on there, but it might be more interesting later, all over 2. So if I think about squaring out the numerator and squaring out the denominator, what I'm going to get in my numerator is 1 plus 2 cosine of 2x plus cosine squared of 2x all over 4. So at this point, we notice that the cosine squared of x is still here, and we need to get that out. And we started with the cosine squared of x, and another one showed up, but that's okay. We can deal with that one more time. So let me rewrite this up here. As I write this, I'm going to just pull a 1/4 to the front. That way I don't have to worry about rewriting this denominator every time and making things a little bit more difficult than they need to be. On the inside here, I'm going to have 1 plus 2 cosine of 2x plus, and now I'm not going to write cosine squared of 2x, but I'm going to make the substitution here using the power reduction formula. So what we've got is 1 plus the cosine of 2 times, and I want 2 times, maybe I'll even color code here, what argument I had before, which was 2x. So I want 2 times 2x here. And this is all over 2. So now if I try to simplify that inside a little bit, I'm going to get 1/4 times 1 plus 2 cosine of 2x plus 1/2 plus cosine of 4x all over 2. Okay, I've got things written out somewhat nicely here. That way I can now redistribute this 1/4 and combine like terms and get everything written in one string here. So I'm going to have 1/4, this is just distributing now, plus 1/2 cosine of 2x plus, this will be 1/8, and then we'll have plus 1/8 cosine of 4x. Sorry, that's getting a little squeezed in there. Let me write that a little cleaner. All right, and now I can combine my 1/4 and my 1/8, and we will get that that is 3/8 plus 1/2 cosine of 2x, whoops, 2x, plus 1/8 cosine of 4x. So there we go. We have achieved our goal, which was to rewrite cosine to the 4th power of x so that there was no powers of sine or cosine greater than 1. There we go. All right, just another example here of using the power reducing formulas. We want to just prove this identity here instead of trying to accomplish some goal. So we're going to show that this is true. So the first thing that we'll do is look at this left-hand side here, and I'm going to rewrite this as sine of 2x times, well, I guess I don't need a big parenthesis quite yet, times sine squared of 2x. And now what I can do is use my power reduction formula on the sine squared of 2x. So I don't have one for a cube, but I can just factor off a sine of 2x and get this down to a sine squared of 2x and then use the power reduction formula there. So now what we're going to have is sine of 2x times, now the sine squared is this formula here. So we're going to have 1 minus the cosine of 2 times whatever we had before. And what we had before was 2x. So here's where we need to be a little bit careful, making sure that we're getting our arguments plugged in correctly, and this will all be over 2. Now as I rearrange things a little bit, in fact, I think we're pretty close here. I'm going to have sine of 2x times 1 minus cosine of 4x all over 2. And then I could think about factoring or rewriting this rather as 1/2 minus cosine of 4x. Oh, there's a 1/2 in here still. Cosine of 4x. So that's just splitting kind of this denominator apart and rewriting this as a difference here. And then I could factor a 1/2 to the front here, to the front of everything, and get 1/2 sine of 2x times 1 minus cosine of 4x. And there, I think that we have it. Yeah, so the final form is just written with another pair of parentheses here, which aren't totally necessary, but we'll write them in to make it match visually. So I've got 1/2 sine of 2x times 1 minus the cosine of 4x. So there we go. Our identity has been proven. All right, next we are going to take a look at the half angle formulas. So here we might need to find or evaluate some angle at something like 15 degrees, which we do have a way to deal with 15 degrees using sum and difference formulas. But we could also use the half angle formula as well, because we know something about 30 degrees and we are looking for something that's half of that common angle. So what we're going to do here is we're going to let theta be equal to alpha over 2, where potentially theta is some angle that we know. I'm sorry, alpha is some angle that we know, and we're dividing it by 2 to get the half of that angle there. So what we're going to do is rewrite sine squared theta as sine squared alpha over 2 is equal to 1 minus cosine of 2 times alpha over 2 all over 2. And now maybe you can see why alpha over 2 is what we want, because it gets rid of the double angle on cosine there for us. So we're going to have sine squared of alpha over 2 is equal to 1 minus the cosine of alpha over 2. And then we'll take the square root of both sides. And don't forget that when we take a square root, we need a plus or minus, and then we'll have to think about the situation that we're in as we're solving problems. Which quadrant is theta in? Which quadrant is alpha over, or which quadrant is alpha in? Which quadrant is theta in? And all that good stuff. So what we get at the end here is that sine of alpha over 2 is equal to plus or minus exactly what it says there, 1 minus cosine alpha all over 2. So there is our half angle formula for sine. Now we will do cosine. It will be a very similar process here. So we're looking at cosine squared of not theta, but of alpha over 2. And this will give us 1 plus the cosine of just alpha. So just like it did last time, we're going to multiply 2 times alpha over 2 to just get alpha here. I'm just skipping that step, all over 2. And then we'll take the square root of both sides, and we'll get that the cosine of alpha over 2 is equal to the plus or minus square root of 1 plus cosine alpha all over 2. So there is our half angle formula for cosine. Okay, and now to get tangent squared theta, what we're going to do is just use what we knew about, maybe I'll color code here, about sine squared of alpha over 2 and cosine squared of alpha over 2. So before we take the square roots here, so just rewriting, in fact, maybe I'll just keep it in blue here. What we're looking at is tangent squared of alpha over 2 is going to give us sine squared alpha over 2 over cosine squared alpha over 2. And then I can just make those substitutions. So sine squared of alpha over 2 is 1 minus the cosine of alpha. And the cosine squared of alpha over 2 is 1, and this is over 2, sorry. This is over 2. And then the cosine squared is 1 plus cosine alpha over 2. And again, just like it happened before, these 2's will undo each other, and what we're left with is just 1 minus the cosine of alpha over 1 plus the cosine of alpha. So there we go. There is the tangent version as well. So now if we need to find some half angle, we've got these formulas at our disposal as well. So let's take a look at an example here. We want to find the sine of 15 degrees using a half angle formula. So like I said earlier, we can find the sine of 15 degrees using other methods. We can use the sum or difference formula. I could do like sine of 45 degrees minus sine of 30 degrees, and that will work just as well. Now our answer will look a little bit different, but that's okay. They are equivalent answers. So what we're going to do here is look for the sine of 30 degrees over 2, since that says the same as sine of 15 degrees, and that's why this this version is helpful. I know this is going to be plus or minus the square root of 1 minus cosine. Now alpha is just the portion in the numerator here, and this is why it's helpful, because we should hopefully know something about the cosine of 30 degrees. which allows us to evaluate this right-hand side. All right, so now we're going to determine if we want to use the positive or the negative version here. And since sine of 15 degrees is positive, since sine of 15 degrees is positive, it's this very shallow angle here, we should be getting the positive version here. What we have now is the positive square root of 1 minus, and now the cosine of 30 degrees is the square root of 3 over 2. So square root of 3 over 2, all over 2. And now we just have some arithmetic to do here. So I can rewrite this as the square root of 2 over 2 minus square root of 3 over 2, all over 2. Whoops, all over 2, and I need to make my root symbol bigger here. So then that will give me the square root of 2 minus the square root of 3 all over 2, which is going to give me the square root of 2 minus the square root of 3 all over 4, which then if I take the square root of the numerator and the denominator separately, it's going to give me the square root of 2 minus the square root of 3 all over the square root of 4, which gives us our final answer here of the square root of 2 minus the square root of 3 all over 2. So there we go. We've got the sine of 15 degrees here using the half angle formula. Like I said, had we used a sum or difference, or specifically a difference formula here for sine, we would have gotten a different looking solution, but the evaluation would be exactly the same. If you plugged them into a calculator, you would get the exact same value. All right, moving on, we will take a look at this next example. So here we're given that the tangent of alpha is equal to 8 over 15, and that alpha is in quadrant 3. And what we want to do here is find the sine of alpha over 2, the cosine of alpha over 2, and the tangent of alpha over 2. Now, down here in the bottom right, I've got our different forms here that we can use as we go. But let's take a look at the situation here. And there's some extra bits that we need to think about. So first I'm going to start by drawing a unit circle. And I know that tangent is in quadrant 3. So let's drop in an angle over here in quadrant 3. So here we're looking at this angle, alpha is what we're calling it. This angle alpha, but what we want to do is find something about alpha over 2. So the first thing we need to think about is which quadrant, maybe I'll even write this down, which quadrant is alpha over 2 in. We know that it ranges, from 180 degrees to 270 degrees. So if we halved 180 degrees, we would just be back up at 90 degrees. And if we halved 270 degrees, we would be at 135 degrees. Which means that if we have some alpha that's in quadrant 3, half of it has to be in quadrant 2. In fact, it'll be somewhere in this top portion of quadrant 2. And anything that is in quadrant 4 will actually end up in the bottom half of quadrant 2. So it's always important to think about what quadrant is alpha over 2 going to be in, depending on which quadrant alpha is in. So here we can say that alpha over 2 is going to be in quadrant 2, and that will be important to think about. What sign does sine have on it in quadrant 2? What sign does cosine have in quadrant 2? And what sign does tangent have in quadrant 2? So there's our first bit of important information here. And now, since we're going to need the cosine of alpha in all of our formulas here, let's figure out what the cosine of alpha is. Let me just maybe erase some of my other thinking here. Okay, so we're looking at this angle alpha. Let's drop in our reference triangle so we can get our reference angle here. And I know that tangent is 8 over 15. Tangent is opposite, and that's going to be a negative 8 over adjacent, and that's going to be a negative 15. So using the Pythagorean theorem here, I'm going to get that this other side, so let's work it out. Negative 8 squared. Let me write this a little bit better. This hypotenuse here, hypotenuse h, is equal to the square root of negative 8 squared plus negative 15 squared, which is going to give us 17. So this hypotenuse here is positive 17. I'll write that a little better. Okay, then that tells us that the cosine of alpha is going to be adjacent, negative 15 over 17. So this is the value that we're going to need as we plug things in down here. Okay, so that is our goal now. So we want the sine of alpha over 2, and this is going to be plus or minus the square root of 1 minus cosine alpha, which is negative 15 over 17, all over 2. The first thing I like to do is decide if we need the positive or negative version here. So remember, all A, smart, trig, class, we know that sine is positive in the second quadrant. Remember, we're looking at alpha over 2, not alpha. That's why we're looking at quadrant 2. But it is positive. Sine is positive there. So we will choose the positive version here. Now, as to do a little bit of arithmetic, we are going to get the positive square root, and I can write this as 17 over 17 plus 15 over 17, all over 2. So this is going to give us the square root of 32 over 17 times 1 over 2. That's the same as dividing by 2. These will cancel, and we'll get a 16 up there. So this is going to give us the square root of 16 over 17, which is 4 over the square root of 17. And if I rationalize my denominator, we'll get 4 times the square root of 17 all over 17. So here is the sine of alpha over 2 in this situation here. All right, next we will find the cosine of alpha over 2. So we'll use this formula here. So what we want is, maybe we'll switch colors just for fun, is plus or minus the square root of 1 plus cosine of alpha over 2, which is going to be negative 15 over 17. All over 2. And now let's think, do I want the positive version or the negative version here? Well, since cosine is negative in quadrant 2, we're going to choose the negative version. So let's try and not forget to write the negative every time here. It's easy to forget to write the negative. Maybe that's a good reason to decide last, but I usually like to think first. So then we're going to have 17 over 17, just rewriting my 1 with a common denominator, with this 15 over 17 here, all over 2. This is going to be the same as negative square root of 2 over 17 times 1 over 2. Then those 2's will cancel, and we've got the negative square root of 1 over 17, which is going to be negative 1 over the square root of 17. And if I rationalize that denominator, we'll have negative square root of 17. Write that a little better. Over 17. So there is our cosine of alpha over 2, negative square root of 17 over 17. And the last one here, we want to get the tangent of alpha over 2. So maybe we'll switch colors just for fun. I want to write this as plus or minus the square root of 1 minus cosine of alpha, which is negative 15 over 17 over 1 plus the cosine of alpha, which is negative 15 over 17. Now I can let's figure out if we want the positive or negative version here. In quadrant 2, the tangent is negative, so we want the negative version here. So we're getting negative square root of, 17 over 17 plus 15 over 17 all over 17 over 17. I'm just rewriting these ones, the 17 over 17, to get a common denominator, minus 15 over 17. This is going to give me negative square root of 32 over 17, excuse me, over 2. Whoops, I meant this to be a 17 here. I carried away. 2 over 17, which is going to give us the negative square root of 32 over 17 times 17 over 2. That's going to reduce down to 16. Those are going to cancel. I'm going to have negative square root of 16, which is negative 4. How about that? That one worked out real nice at the end there. So the tangent of alpha over 2 in this situation is negative 4. So there we go. All right, there are all of our new formulas. So now it is time to practice. Good luck with the homework. If you have any questions, please let me know. I'm always happy to help, and I'll see you in our next video.